And flight engineer Andre Kalpers is busy with a software update on the space station's agricultural camera. Flight engineer Don Pettit is scheduled to be back at work in the Destiny Laboratory preparing the a workspace at the Microgravity Sciences glove box for the BASS experiment. And BASS is an acronym for Burning and Suppression of Solids. It's a physical sciences investigation into both the burning and the extinction characteristics of a variety of fuels in space. The principal investigator for BASS is Dr. Paul Furcool. He's a staff scientist at the National Center for Space Exploration Research in Cleveland, Ohio. And he joins us on the phone this morning from the Telescience Support Center at the NASA Glenn Research Center. Dr. Furcool, welcome. It's some excitement for you today to get to see your experiment being prepared for use.
Oh, thanks. I'm glad to be here, and I'm glad to be talking with you.
Is this your first experiment to be performed on orbit?
I participated in an experiment about 15 years ago as a co-investigator, but this is the first time I'm a principal investigator.
Uh, for you, how did you become interested in this field of burning things?
I think, like many of my colleagues here at NASA, I had a good mentor when I was in college, and I had an engineering background, engineering degree, and there was an opportunity to do work at NASA here in Cleveland. I went to school at Case Western Reserve University, and my advisor at Case Western Reserve had a position here at NASA for me to do some work, and so it sort of was just a fortuitous sequence of events that led me here in an area that I really wanted to work in, namely the space program.
Do we know much about how things burn differently in space than the way they burn on Earth?
We actually do know quite a bit. We know that on Earth we have buoyancy, which is the tendency for hot air to rise, whereas in zero gravity there is no buoyancy. And on Earth we can do testing in drop towers and aircraft, zero gravity aircraft, to get some idea. So we have a good idea of how things behave in zero gravity. But what is lacking for us is actual experimental data for long duration burns, and that's what we hope to gain in the space station tests we're doing.
Now, there have been experiments with burning previously on the station and on shuttle missions too, but this one is going to have for an more extended period of time?
That's certainly true. There have been other early experiments, even going back to the 1980s. There were some simple solid fuel combustion experiments done. They were limited in scope. They were generally very small samples and not very numerous. So what we hope to do, and there have been other tests as well that have looked at combustion on either the space shuttle or the Russian Mir space station. But this one, we're trying to build a database. We have many samples we're flying, actually a total of 41 samples. We're going to burn multiple times and try to really build a database and get some experimental knowledge of how things behave for long durations in zero gravity.
Is there a central hypothesis that's driving your operations here?
There is. The basic applied hypothesis is that we believe that under certain conditions, a material in zero gravity will actually be more flammable than it is in normal gravity. And there's some theoretical basis for this, and we've done some drop tower tests to begin to verify this phenomenon. The testing we do right now to select materials for use in space for the astronaut safety, all the tests are done in normal gravity on Earth. And so it's always assumed that normal gravity tests will be conservative and that things in space will are less dangerous. But again, it turns out our hypothesis is that there may be conditions where the opposite is true, that actually in space things could be more dangerous, and of course that's a concern to NASA.
I mentioned that Don Pettit is going to be working this morning setting up the hardware for where this experiment will be conducted. Can you describe what hardware is involved here? What work is Don doing today?
Sure, he's working in a facility called the Microgravity Science Glove Box. It's essentially a large glove box that you might see in an ordinary laboratory with glove ports and a fairly big working volume. Our experiment will plug into that volume, so it's a level of containment. And our experiment is relatively small. It's about the size of an ordinary toaster, and it consists of a flow duct. So there's a fan in our experiment module to generate airflow. We install fuel samples inside our experiment module, which are then ignited, observed with video cameras, and burned through there either to completion or until we decide to put them out.
So there's some, you don't know how long they'll burn.
We have a limit generally of a 2-minute maximum, because within 2 minutes we should be able to reach the information that we need to get. That should be achievable, and we're trying to use our fuel judiciously. So we'll try to have them put out the fuel at that point, so we can continue in the future with additional tests.
At the time that the experiment's operating, then how is the flame lit? I mean, Don's not up there striking matches, is he?
That's correct. He'll be remotely igniting them. Actually, we use a hot wire igniter. So again, think of a toaster, and you have heated elements in there that glow red hot when you apply electrical current. So that'll be the same idea. We have a small loop of igniter wire that'll glow red hot, or almost actually yellow hot, which will be in close proximity to the fuel sample, and then ignite it.
Now, you said there were 41 different samples. Each of them is going to be ignited multiple times.
That's correct. Actually, some will be one-time use, but the vast majority will be multiple-use samples.
And when are the first data takes going to begin?
We begin operations on Friday.
This week?
That's correct.
Now, I take it that there aren't any experiment samples to be returned, since they would have burned, I guess. How do you get your data?
Most of our data will be through photos, so either 35mm still camera photos or video images, which will be downlinked every day to us. It will have the full resolution video and 35mm still pictures.
And then your analysis is studying the photographs.
That's correct. We'll basically get flame luminosity data, flame shape, structure, and I guess most importantly, how the flame reacts to different changes in flow, or when we go to put the flame out, how we can extinguish the flame and how the flame reacts as we extinguish it. Then we can use all this information to compare to our existing models and improve them and develop better models as a result.
Is there any way at this point to generalize about what you expect to see?
We expect, again, we've done some tests in zero gravity with these flames. Generally, they tend to be weaker, but it's a big function of the flow speed. So if we blow on them gently, we'll probably get a relatively dim blue flame, and as we increase the flow velocity, it'll start to transition to a brighter blue, and then ultimately yellow and sooty. So that's how the flame will look. We expect, again, there will be some cases that these materials might actually be observed to burn in zero gravity in conditions where we can't get them to burn in normal gravity. So that would be the exciting finding for us. So we've flown some samples that we expect will burn up there that we can't get to burn in normal gravity.
That would certainly be something that would be important to know if there's something that does burn in space that we wouldn't expect.
That's correct. And we've done some drop tower tests which are limited in time, so we're not sure how they're going to go for long duration, but we believe they might actually might burn up there.
At this point, how would the findings that you get, how could they be applied both in space and on Earth?
I guess as far as NASA is concerned, a direct application is for fire safety. Because NASA is very careful about selecting materials, configurations, and is concerned about NASA or astronaut safety. There's an extensive set of tests done on Earth to select materials, and it's all done. All these tests are done in normal gravity. Now, if our hypothesis is proved to be correct, we might need to modify the tests that we do on normal gravity to consider effects and conditions where actually the materials could be more dangerous in space. So we have to revisit the testing procedure that we do on Earth. And more widely applicable are the results of these experiments to models. So again, computer modelers can use these results to develop sophisticated systems and simulations that would apply to many different kinds of combustion systems, not just for these simple fuels and flames, but for wide-ranging applications such as engines, boilers, and so on. Anything in our everyday life that relies on combustion, which, as you could imagine, is much of what we rely upon.
The obvious question that, of course, I saved it for last, how dangerous is it to be setting fires inside the space station?
Well, that's a good question. Generally speaking, we don't want the astronauts to set anything on fire, but this has been carefully designed so there's two levels of containment. So, as I mentioned earlier, the glove box itself is one level of containment. Within that, which is that is a sealed vessel, there's our experiment, which is also a sealed vessel. So it's two levels of containment, and there's no way to set the fuel on fire to ignite it unless all the doors are closed. So there's many safety constraints in place.
And the first of these experiment runs get started on Friday.
That's correct.
Besides, we have one other question that came to us over Twitter from @Karen of Earth, asked, besides rocket fuel, which we know will burn, what else is self-oxidizing and will burn even in a vacuum?
I guess it depends how you define rocket fuel. There's many materials that you can imagine that you have fuel and oxygen pre-mixed. That's how a rocket engine works, is you deliver fuel and oxygen separately to the engine to generate thrust, even in a vacuum of space. So you need to, if you don't have air, like you don't have in space, you need to supply your own oxygen. So you can imagine there's other materials on Earth that can do that, that would also basically ignite and burn in space besides rocket fuel, such as some of the solid rocket engines that are used for the even simple, rockets that you might buy in a hobby store to light off. Those would also ignite and burn in space just fine.
Great. Your experiment gets started, its operations on Friday. Good luck.
Thank you very much.
Dr. Paul Furkul is the principal investigator for burning and suppression of solids, which is a physical science investigation into the burning and extinction characteristics of a variety of fuels in space. He's with the National Center for Space Exploration Research in Cleveland.